Welcome. I'm absolutely thrilled you're here for this explainer. Today, we're going to peel back the curtain on some hidden, high-speed engineering that literally powers our modern world. I mean, we're talking about a specific, truly fascinating class of machinery working behind the scenes. Some of these things spin faster than the speed of sound, turning raw fluid into serious world-moving power. We're talking about turbomachines. So, get ready, because we're going to break down exactly how these incredible feats of engineering actually work. Let's dive right in with something you've definitely seen. A jet engine. Think about the distinct sections here. You've got the compressor pulling air in, the combustor right in the middle, and the turbine at the back. Now, before we get into the microscopic physics of how fluid interacts with metal, just consider this for a second. That combustor, it operates continuously, like a hurricane of fire. And the turbine blades spin thousands of times per minute, literally just inches away. This whole massive assembly, right at its core, is just a beautifully complex turbomachine manipulating airflow.
Here is our quick roadmap for today. First up, what exactly is a turbomachine? Second, producing versus absorbing power. Third, we'll map out the turbomachine family tree. And fourth, turbomachines versus displacement machines. Let's get into it.
Section 1. What is a turbomachine?
Okay, so a turbomachine is basically a device where energy transfers between a flowing fluid, which, could be gas, steam, water, or even just air, and a rotating element. We usually call that rotating part a rotor, a runner, or an impeller. But the real magic phrase here, dynamic action. It's not just holding the fluid like a bucket. The machine forces a really crucial change in the fluid's pressure and momentum. As the fluid hits those specially curved blades, it creates fluid dynamic lift. It's actually very much like air moving over an airplane wing at hundreds of miles per hour. And that powerful lift is what ultimately gets that rotor spinning.
Now, in the real world, these rotating elements look like beautifully complex works of art. A compressor rotor grabs air and squeezes it tight, physically imparting energy into the fluid to drastically raise its pressure. A turbine rotor, on the other hand, does the exact opposite. It takes a high-energy, really fast-moving fluid, like superheated gas, and extracts that energy from it to turn a shaft. So energy can flow from the spinning rotor right into the fluid, or vice versa, from the fluid into the rotor. The blades are engineered to absolute perfection to make that transfer as ruthlessly efficient as possible.
Moving right along to Section 2, producing versus absorbing power.
So turbomachines essentially operate on two distinct pathways. First, you have power-producing machines, like turbines. Here, high-energy fluid comes rushing in, produces mechanical work, and leaves entirely depleted. Then you have power-absorbing machines, like compressors or your everyday water pumps, and this is a perfect mirror image. Mechanical work is forced into an impeller to take a lazy, low-energy fluid and pump it way up into a highly pressurized state. It's just a brilliant, symmetrical loop of energy conversion.
Section 3. The turbomachine family tree.
We can actually organize this family tree by the type of fluid flowing through the machine, starting with three main branches. First, hydraulic turbines. These use water. Think of those massive hydroelectric dams utilizing Pelton, Kaplan, or Francis turbines. Then, we have steam turbines, like the Parsons or Curtis models. These are the absolute workhorses of nuclear and coal power plants, sometimes running at mind-boggling temperatures that actually exceed the melting point of standard metals. Crazy, right? Finally, we have gas turbines, which power our jet engines and natural gas plants. The working fluid you choose completely dictates the machine's design. Take the classic Pelton wheel, for example. It's a perfect example of a hydraulic impulse turbine. High-pressure water shoots out of a nozzle and violently strikes those outer, bucket-like shapes tangentially. And by tangentially, I mean it hits right along the extreme outer edge of the wheel. The sheer physical force required to withstand that constant high-speed bombardment is just immense. It violently throws that heavy metal wheel into a rapid spin to generate power.
Now, aside from the fluid type, engineers also classify these machines by exactly how the fluid moves through the impeller relative to the spinning axis of the shaft. We just talked about tangential flow with the Pelton wheel, but there's also radial flow, where fluid enters the center and is flung outward along the radius, kind of like in a centrifugal pump. And then there's axial flow, where the fluid moves parallel to the shaft. Think of a desk fan blowing air straight forward. That is exactly how a Kaplan turbine operates.
With a heavy-duty centrifugal pump, you can really clearly visualize that radial flow. Fluid is sucked into the very center of the housing, and the internal impeller violently spins it around, using centrifugal force to fling it rapidly outward and up into a large discharge pipe. It's a fantastic, concrete example of radial flow hardware out in the field doing the really hard work of absorbing power to move heavy fluids at scale.
To round out our family tree, These machines are also grouped by the condition of the fluid. Specifically, is it an impulse turbine, where a literal high-speed jet of fluid blasts the blades, or is it a reaction turbine, where the blades are fully submerged and driven by the pressure differences flowing entirely across them? And when you combine that with whether the spinning shaft sits horizontally, vertically, or inclined, well, every single one of those details completely dictates the machine's ultimate design and efficiency.
Section 4. Turbomachines versus positive displacement machines.
All right, time for an engineering showdown. In one corner, we have our turbomachines. They use dynamic action to spin continuously at incredibly high speeds, sometimes tens of thousands of RPMs, and they do it with almost zero vibration. It's a remarkably simple, dynamic design, though. To be fair, overall efficiency can sometimes take a hit. Now, in the other corner, we have positive displacement machines. Think of your car's internal combustion engine. They physically trap and force fluid to move. Because of those violently pumping pistons, you get lower speeds, higher vibration, and way more moving parts. But you get a massive boost in comparative efficiency. So you're essentially trading smooth, high-speed simplicity for a complex, vibrating, highly efficient punch.
So, as we wrap up this explainer, I really want to leave you with a question to think about. How many invisible turbomachines have you already relied on today? Was it the water pump that pressurized your morning shower? Maybe the steam turbine at the local plant that generated the electricity for your coffee maker? Or maybe even a gas turbine flying right overhead. These machines are literally the silent, high-speed heartbeats of our modern infrastructure. Keep observing, keep learning, and I'll catch you in the next explainer.